The act of reaching for a glass of water requires a massive, synchronized firing of signals across your nervous system. When that signaling network begins to break down, the earliest evidence is physical. This loss of control is a hallmark of Parkinson's disease. It is a progressive, neurodegenerative disorder that directly targets the central nervous system, slowly stripping away the brain's ability to coordinate basic muscle movement. The clinical markers of this progression are clearly defined. Patients experience severe muscle stiffness, a persistent slowness in their everyday movements, and pronounced rhythmic tremors. These outward symptoms occur because the brain's internal timing mechanisms are misfiring. The motor cortex attempts to send clear physical instructions, but the routing network is compromised along the way. Every stiff gait and involuntary tremor we observe on the outside traces back to a highly localized, microscopic point of failure deep inside the patient's neural circuitry. To find that specific point of failure, we have to look past the macroscopic muscle groups and examine the microscopic gaps connecting individual brain cells. Neural communication relies on a strict unidirectional flow. An electrical signal fires, moves down the cell, and must cross a physical gap, the synapse, to reach the next neuron in the chain. Because an electrical pulse cannot physically jump this gap on its own, it requires a chemical messenger. In the motor control circuits, that essential messenger is a neurotransmitter called dopamine. The biological root of Parkinson's disease is a severe and progressive decrease in the brain's ability to produce this specific neurotransmitter. Without sufficient dopamine production, the synaptic gap becomes a dead end. The few molecules that are released are too sparse to trigger the receiving cell, and they fade out in the void. When dopamine levels collapse, that one-way communication chain is severed. The brain's instructions never reach the muscles, resulting directly in the motor failures we see in the patient. Medical science cannot easily restart a failing brain's dopamine production. Instead, treatment relies on pharmacological interventions like selegiline, a medicine designed to intervene directly in the synapse to modulate the remaining dopamine environment. This data table records the precise quantity of dopamine present in the synaptic cleft over a microscopic 5-millisecond time window. We are given two specific conditions to compare: a patient's measurements in the absence of selegiline and their measurements in the presence of the drug. To understand the drug's mechanism of action, we need to translate these temporal measurements into a visual curve. By plotting this exact data, we can mathematically prove how a targeted drug compensates for a biological deficit it cannot physically replace. This chart graphs the dynamics of the synaptic cleft. Our x-axis tracks the time from 0 to 5 milliseconds, and the y-axis tracks the quantity of dopamine from 0 up to 100 micromoles. At 0 milliseconds, we start our plot. The initial quantity of dopamine released into the synapse hits a baseline of 100 micromoles in both scenarios. In the absence of treatment, that volume rapidly collapses. At 1 millisecond, it drops to 75, then down to 60, 50, and plummeting to 20 micromoles by the 4th millisecond. At exactly 5 milliseconds, the untreated synapse hits absolute zero. The dopamine is entirely gone. This steep mathematical curve is the visual representation of rapid clearance. The nervous system is actively sweeping the neurotransmitter out of the gap almost as soon as it arrives. When you pair aggressively rapid clearance with an inherently low initial production, successful neural transmission becomes mathematically impossible. The untreated synapse is effectively a leaky system. The chemical messenger vanishes before it can secure the connection. Now we plot the second dataset, mapping the exact same timeline but in the presence of selegiline. Returning to the chart, we have an identical starting value. At 0 milliseconds, there are 100 micromoles of dopamine, but here we see significantly higher retention. Over the next 4 milliseconds, the quantity drops slowly to 90, 80, 75, and 70 micromoles. At the 5 millisecond mark, the effect is stark. Where the untreated synapse was completely empty, the treated synapse retains 55 micromoles of dopamine. Looking at the completed graph, we can confirm that the overall quantity of dopamine decreases in both scenarios. The critical difference is the rate of decrease. When selegiline is present, that clearance rate drops drastically. Mathematically, we have a shallower curve. Biologically, this means the dopamine molecules linger and bounce within the cleft, rather than being instantly flushed out. Selegiline functions strictly as a temporal tool. It buys the brain time by preventing the premature removal of the messenger. The specific mechanism driving this data is chemical blocking. Selegiline acts to prevent local enzymes from either rapidly degrading the dopamine or pulling it back into the original firing cell. This does not cure the underlying lack of production. Rather, it aggressively optimizes whatever minimal dopamine the patient still produces. Because the molecules stay trapped in that one-way gap for an extended period, they finally have the required time to lock into the receptors on the postsynaptic neuron. The threshold is met. The signal successfully surges across the gap and races down the axon toward the motor cortex. By mathematically and chemically slowing the clearance of dopamine, we successfully restore the continuity of the body's motor control circuit. The final conclusion from our dataset is definitive. Selegiline maintains a significantly higher quantity of dopamine in the synaptic cleft over time. That microscopic retention directly enables the attenuation of the outward physical symptoms we observed earlier. The rigid, tremored state associated with neural misfiring is mitigated, allowing the patient to return to a more relaxed, fluid posture. This is the exact purpose of targeted pharmacology, applying rigid chemical science to manage chronic conditions and directly improve the patient's daily quality of life. By calculating the precise temporal dynamics of a single microscopic synapse, we bridge the gap between abstract clinical data and tangible human health.